Hi, my name is Braden Marconi, and today I'll be presenting Physics 2212's Lab 6 Magnetic Molasses. The purpose of this lab was to observe and evaluate how a magnet falls slower when dropped through an electrically conductive tube. First, we performed the experiment in the real world and observed what happened, and then we modeled this interaction in glow script. And our results were that we found the average falling time in the real world was around 1.36 seconds, and the model's predicted falling time was 1.065 seconds. The fundamental principles used in this lab were the Biot-Savart law, which calculates magnetic field exerted by a magnetic dipole moment at any point in space, Faraday's law, which relates the EMF to the change in flux, Ohm's law, which is uh, V equals IR, Lenz's law, which relates current in the length that is traveling across the magnetic field to the force exerted on what you're analyzing, and Newton's law with the second law of F equals ma, and the third law of every force has an equal and opposite reaction force. So here you can see your experiment where we wrapped a tube in aluminum foil and we dropped a magnet through it, and we measured how long it took to go all the way through. The system was the bar magnet in the tube, and the surroundings was everything else. On the left here, you can see the physical properties of the magnet in the tube and our trial and our results. These are our results. Our average time was 1.36 seconds. After completing the experiment, we modeled the interactions using GlowScript. So our first slide of our code, we are establishing our physical constants for the tube, the magnet, and then the universal constants. Next, we're establishing a function that calculates the magnetic fields exerted from the magnet using the dipole B functions, and we're also establishing a function that calculates the flux going through a singular cross-sectional ring of the tube from the magnetic field by the magnet. And next, we're using Ohm's law to calculate the current flowing through those rings using flux that we calculated in the previous slide. And then we're using the current to use Lenz's law to calculate the force that is being exerted on one ring by the magnet. Then we're summing up all those forces of all those individual rings and then using Newton's third law. And we know that the ring exerts an equal and opposite force on the magnet, meaning the forces the magnet exerts on the ring equals the force the ring exerts on the magnet. So then we can sum up all those forces that are acting on the magnet, which are gravity and then also the magnetic field, to get the total force that's being exerted on the magnet. And using Newton's second law, we can extrapolate from the acceleration by velocity and then the position of the magnet and iterate over time to find the position of the velocity of the magnet as it falls into the tube. So here are our results. We have a graph of velocity versus time. You can see that I've labeled as the magnet is entering and exiting, the force of gravity overcomes the force of the magnetic field, which causes it to accelerate. And this is because there's less tube on the top when it's entering or less tube on the bottom when it's exiting to experience a flux and then create a magnetic field. So there's just less magnetic force. And then in the middle, there's a material on the top and the bottom to exert a magnetic field. The force of gravity and the force of the magnetic field equal each other, so the velocity is constant during that time. There are a lot of assumptions made in this model. The only forces are from the magnetic field and gravity, and we're assuming that the dipole moment is always aligned with the x-axis of the tube, when in reality it's likely tumbling a bit and it's not always perfectly parallel to the axis of the tube. So the source of error in this model, because our time that we got from this model is 1.065 seconds, which does not match the time in the real world, is that inaccurate magnet timing when we perform the experiment in the real world. Like I said earlier, the magnet could be tumbling and colliding with the sides of the tube, so the friction between the magnet and the walls of the tube, and also inaccuracies from those assumptions. All right. Which color corresponds to clockwise current as viewed from the above and which counterclockwise? And how can you know? So the model, we're assuming that the magnetic dipole moment is pointing up. A current is induced to resist the change in flux. So because of this, the red indicates clockwise and blue indicates counterclockwise. Now, what happens to the dynamics of the system when you flip the magnet around? So the motion of the magnet wouldn't change, but the currents would be flipped because the magnetic field would be traveling in the opposite direction. Now, how's the total time of the tube of the real world system compared to that of the computational system? How might the computational system be made more accurate? I discussed that in previous slides due to the assumptions and errors in the experiment. And then what does the shape of the velocity versus time graph tell you about the force acting on the bar magnet? Once again, gravity overcomes the force of the magnetic field when it's entering and exiting the tube, and then they are equal in the middle of the tube, causing the magnet to have a constant velocity. And finally, what if resistivity of the conductivitors of the conductor were reduced as close as possible to zero? And how would the dynamics of the falling magnet change? So by Ohm's law, decreasing the resistivity, which would decrease the resistance, would increase the current flowing through the tube. And by Lenz's law, increasing the current would increase the force exerted on the magnet, causing it to fall slower. And then what if holes or slots were cut into the tube? How does this affect the ring of the currents in your model? So a cross section of the tube that contains a slot would be analogous to an open circuit, meaning no current would flow through that section, which means no magnetic field would be induced, causing the magnet to fall faster.